Okay, so these are the 4 problems that they want us to look at. Notice that all 4 problems have the same set of directions. Now, let me just say this. I am far more competent and confident with levels of math that precede and proceed this particular level of math. I haven't done Calc 2 in about 10 to 15 years. That being said, let's look at number 45. And again, I'll only do and say as much as I am fairly confident in and with. So number 45, we have this. Now, they want a handful of things from us. And as a matter of fact, let me write down an answer key so that we can make our way there. So here's sort of my answer key. They want us to tell them the radius of convergence, the interval of convergence, where the series converges absolutely, and where the series converges conditionally. Let us fill out these 4 pieces of information and we're done. So first, let's find the radius of convergence and the interval of convergence. We do that by pretty much using the ratio test. The ratio test is far more commonly used in my experience than the root test. So the ratio test says this. It wants you to take the limit as n approaches infinity of a very specific ratio, a sub n plus 1 over a sub n. So a sub n is this. That's a sub n. A sub n plus 1 is whatever you get when you replace all of the n's with n plus 1. So let's build this here. Let's build this expression. So here I have the limit as n approaches infinity. Now the numerator is all of this here, but all these n's become n plus 1. And the denominator is the original expression that is within the series, which is this part here. And we'll put some absolute value bars around them. Now recall that instead of dividing ratios, we can multiply them, but you'd have to reciprocate the denominator. So let's do that. Now let's do some seriously heavy algebra where we rip apart some of these pieces into smaller pieces and where we shuffle and reorganize pieces to our liking. So notice that everything is exactly the same. I haven't cheated. Everything is still inside the absolute value bars. I decided to take this expression and rip it apart into 2 smaller expressions. The same for this one here, that is down there. And I just shuffled some pieces around conveniently. The n is still there, and underneath it, I decided to put the n plus 1. And then I put that one here, right there. See, they're all there. And the reason I broke these apart accordingly is because you see that these go away and these go away. So let's see what's left. So that's what we're left with. Now, what I want to do is, whatever does not depend on n, I'm going to sort of take out of the limit because the limit only involves n. So these pieces here, I'm going to take them to the outside. So here's what I'm left with. And notice that I kept the absolute value bars on the x plus 4, but not the 1/3 because the absolute value of 1/3 is just 1/3. Looking at this part here, as n approaches infinity, what number does this ratio get close to? Well, we use our prior knowledge of this concept, of these concepts, and we know that this is just 1 because the numerator and the denominator grow at the same steady rate because they both have a degree of 1. So as n gets really big, it's essentially a big number over that same big number. Yeah, the plus 1 sort of loses its influence as n gets really big. So I use prior knowledge to just jump to the fact that this here equals 1 and everything else stays the same. And notice that I've dropped the limit notation because I applied the limit to this entire expression, which is just 1. So here's what I have. Let me go up here now. So we have equals 1/3 absolute value x plus 4. So I have taken this. I have applied the ratio test to this, and this is what I got. Now, what exactly do we want to have happen? We want the value that we obtain from the ratio test. We want it to be less than 1. You always set this less than 1. set it less than 1 pretty much every time you apply the ratio test in this context. Now we solve this inequality. Multiply both sides by 3. Like this. And then your freshman math teacher told you just to take this inequality, which if the little thingy is pointing like this, then you have the following setup. They probably did not tell you why. We could get into that, but for now, again, we're just chasing a grade, right? So this is the setup for it. Now subtract 4 from all 3 sides, and we get the following statement. So here, this is what we call our absolute interval of convergence. So let me actually go here, and let me update this. So this here, that's actually where your series converges absolutely. So I just knocked that out. That takes care of that. Whatever this is, that goes here for converges absolutely. Now, let me ask you this. -7 and -1, how far away are they? They are 6 units away. 6 units. Cut that in half, that's 3. That is your radius of convergence, 3 spaces. Because this is actually centered at -4. If you notice, if you set this equal to 0 and solve, you get -4. -4 is sort of the center. And from -4, you span out 3 spaces left and right to obtain these values. Another way of finding the radius is at this point here. This is going to be your radius r if the x has a coefficient of 1. Whatever the coefficient of x is, you divide it into that number to get r. But again, a more traditional way is whatever your interval is, find how far away these are from each other, and that distance gets divided by 2, and that'll tell you the radius r. So notice we're halfway done already. Now we just have to find the interval of convergence and where it converges conditionally. And to find the 2 remaining pieces, we depend on this here. So what we want to do now is take the endpoints, take the 2 endpoints and test them. So let's test. Let's test -7 for x. So let's pretend that x equals -7. So take -7 for x and plug it into the original problem. If I plug -7 right there, it's -7 plus 4, which is -3 to the n. And that -3 to the n, let's write this down. So we have the series n equals 1 to infinity, -3 to the n over n times 3 to the n. You could combine the 3's, not because they're both 3's, but because they have the same power, which is n. And you'd get -1 to the n, right? Because the -3 divided by 3. Now, it is a matter of recognition. This is what we call the alternating harmonic series. And we use prior knowledge and facts and rote memorization to recall that the alternating harmonic series, that series converges conditionally. It converges conditionally. So here for converges conditionally, we can say that this happens at, for sure, x equals -7. How did I know this? Again, it's a matter of just memorization at this point. Now let's test x equals -1, the other endpoint. Let's test the other endpoint, -1, into the original problem. -1 plus 4 is 3. That would be 3 to the power of n. But 3 to the power of n would knock out 3 to the power of n in the bottom. So you're essentially left with 1 over n. And we know for sure that that's the harmonic series, and the harmonic series diverges for sure. It diverges. It's no bueno. So we do not have conditional convergence at -1. We only had conditional convergence at -7. So that takes care of that. Now, what is the overall interval of convergence? Well, it's at least this much. The only difference is, do I put a little bar here? Yes or no? Do I put a little bar here? Yes or no? Where did it converge conditionally? It converged conditionally at -7. So for that reason, I put a little bar here and I'm done. Now let's recap exactly what happened. I took the original problem and I hit it with the ratio test. And that's when I replaced all the n's with n plus 1. And I got this here. I did all kinds of crazy algebra. And it led me to this. And then whatever this is, you always set that less than 1. Always less than 1 and solve. And whatever you get, that is going to be your absolute convergence. So notice that that's actually the first thing that I found, the absolute convergence, which I got from all of this here. And then I asked myself, how far away are these numbers from each other? That distance was 6. Cut it in half. Boom, that gives you the radius of convergence. And then you test the two endpoints. You test them as we did, and that's where you might have to recall some previous information. And I tested both endpoints. If any of them converged conditionally, then I write that down and I make note of that because that's what they want. And then wherever it converged conditionally, I put a little bar on it, and that's what gave me the overall interval of convergence. So this is the first thing that I found. Then I found this, and then I found this, and then I found that. And notice that the interval of convergence is basically your converges absolutely interval, with the exception of sometimes these have a quality given to them based on where it converged conditionally. So is all of this stuff very confusing? Oh, of course it is. But you have to do more and more and more examples.